Hello, and welcome to the Satellite Image Deep Learning Podcast. I'm Robin Cole, and it's my pleasure to present another technically focused episode in the series. In this episode, I catch up with Nathan Kundtz to learn about the creation and use of synthetic data in training machine learning models. Nathan has a PhD in physics and over 40 peer-reviewed papers and 15 patents to his name. As a serial entrepreneur, he has successfully founded multiple companies and raised over $250 million in venture capital funding. This conversation was a deep dive into the fascinating topic of synthetic training data, and I personally gained many valuable insights from Nathan's wealth of knowledge and experience. I hope you enjoy this episode. Hi Nathan, how are you doing?
I'm well, Robin. It's a pleasure to be here with you.
Fantastic. I'm really looking forward to diving into this topic, synthetic imagery. Maybe you can get the ball rolling just by telling us what it is and why it's important.
Yeah, absolutely. So synthetic imagery is really, the need for synthetic imagery is really driven by the importance of using artificial intelligence across a whole range of applications, but I think today, especially in satellite imagery analysis. So there's just so much imagery now being generated by both commercial and government resources that it's literally impossible to have it all reviewed and analyzed by humans. And so almost all of the insights we get from that data has to come from computer vision and automatic capabilities. And the tools that we use to do that in AI are trained using data sets. So artificial intelligence, I sometimes joke, is just software, but instead of writing it in some programming language, we write it in data. And so the performance that we achieve is really based on the data that we have access to. And when you get into real world environments, data access, it turns out, is really, really difficult. And we can spend more time on each of these, but some of the things people run into are rare events, rare scenarios, rare objects. You can collect a lot of data before you see even a few examples of some critical things. Imagine trying to detect forest fires. You've got to take a lot of data before you start to find those. And that becomes a real challenge if you want to build algorithms to do that kind of detection. But the reason that we originally actually founded the company was because of the systems engineering problem that shows up when you haven't yet even deployed a satellite.
Right.
So I come from a physics background. I have PhDs in physics, and my first company was a hardware company producing electronically scanned antennas for satellite communications. And I was used to what is called a model-based design workflow for engineering. You simulate the environment, you use that to drive what you want to build. And I was really struck that in these imagery applications, you really couldn't do that. You had to make a best guess, and the business models were often, hey, we're going to raise $100 or $200 million, build satellites for a couple of years, launch them, collect data for 6 months. Then we'll figure out what kind of algorithm we can build. And that has obvious problems, both from a technical and business perspective. So an alternative to doing those things is to use simulated or synthetic data, where you are simulating seemingly real world environments in order to ask the question, what would a sensor see? But then doing that at scale with a lot of diversity, and in so doing, creating a stand-in for those real world data sets without the need for that scenario to have ever happened or that sensor to have ever existed.
Right. So you can simulate what a satellite will image even before it's being built, just based on an understanding of how it will be designed and the scene itself. I'm quite interested how you guarantee that if something is rare, how you can reproduce it if you've only got a couple of examples. What's the general methodology there?
Yeah, absolutely. And in some cases, we have zero examples, right? Complete zero shot. So, and I think in answering this question, I should distinguish between two different types of data generation that are both prevalent today. One is what's called generative AI. It's a term that's sort of new, a very exciting field where you use imagery that you have and then a prompt or some other approach, and you generate more. And that approach purely doesn't do a good job of creating things that you've never seen before, because almost by definition, the objects that you're going to create have to be resident in the data set that you trained that original AI algorithm. on. Our approaches focus on physics-based simulation somewhere in the core. Now, we use generative techniques as well and things like domain adaptation. So the complete pipeline involves a lot of different steps. But foundational to introducing new information to the data, and essentially the way that we're able to address this, hey, we've never seen it before or never seen it before with this sensor, is that we are actually doing a physics-based simulation of that environment. So that means we have a 3D model. We actually define things like reflectance curves and emissivity of surfaces, temperature of surfaces if we're getting into kind of infrared. Connectivity, if we're talking about radar returns, et cetera. And then by actually simulating that environment, we could have, it's possible that it doesn't exist or won't exist, but we can still anticipate what we would see from a sensor.
Right. And these models, have they been developed recently, or are these models that have evolved over decades?
Yeah, the physics-based models are things that have developed over decades. So, like, we have a terrific partnership with Deersig out of RIT. They've got about 30 years of heritage in doing really, really solid physics-based modeling of satellite sensors. We also use open source rendering engines like Blender, Unreal Engine, et cetera, as well as partnerships for like X-ray simulation. We've got our own synthetic aperture radar simulator. So we use a lot of different simulation tools. We try to actually avoid writing our own whenever possible. But what we find is that those tools really are always designed to be run by people that are domain experts. So you have, if you have a tool that's sort of meant for infrared simulation, it's kind of like somebody with that electrical engineering degree and optics is sort of running it and defining what they want to see. Same thing for radar, right? You're going to have a radar scientist that's actually running that tool. And so because of that, they're almost never very usable by a computer vision engineer, right? Computer vision engineer already has a PhD. They don't need another PhD, or they don't want to have another PhD in order to address synthetic data. So a lot of what's been missing is the connectivity between those two users, right? So how do you get the skills and knowledge out of somebody with 3D modeling and simulation expertise or deep domain expertise, and then have them be able to, broadly stated, deploy that knowledge into something which can be really used by a computer vision engineer.
Right. Okay, that's really a good background to the algorithms themselves. I'm curious about the general capability. Can I simulate an entire country, or I guess that's probably not practical. What kind of practical bounds are there on the size of scenes that you can simulate?
I mean, it depends on the mesh size that you want for that country, right? Yeah. So at some point, each of the simulations, there's a limitation in terms of compute and system memory. In terms of what that means physically, that will depend on what's being simulated, what resolution it's being simulated at. Yeah. So it's not an easy question to give a single answer to. We do very large simulations sometimes, certainly tens of kilometers on a side, sometimes hundreds of kilometers on a side. For instance, with the work that we've done with Planet and hyperspectral simulation, we have very, very large areas that are being simulated. But they're doing that. The sensor has a fairly low resolution, right? It's meant for spectral resolution as opposed to spatial.
So there's a sort of practical limit based on a couple of factors in terms of spectrum and resolution, and presumably sort of complexity of the scene as well. Okay.
That's right. And to be clear, we've done everything from literally microscopic scenes, right? So, getting down into microns across some of the feature sizes, all the way into, geospatial scale. So, the domain can vary quite a bit.
Okay. Well, I'm really keen to dive into the implications for the machine learning practitioners as well. And you can feel free to sort of make up scenarios, etc., based on your own experience without giving away confidential information. But what are the practicalities if I literally come to you and say, I've got 10 images of something in such and such a place, and I need a model that's 90% accurate? Tell me how much data I need to simulate, and how would you guarantee that I will hit that accuracy in the real world? What does that whole process look like?
Sure. Well, first of all, so just like you wouldn't be able to guarantee like a particular performance score from labeling real data, like we don't, it's not a, hey, for sure you hit this. And a lot of problems, you got to figure out how hard the problem is in the first place, right?
Mm-hmm.
So there's a lot packed into that question. So let me see if I can separate a few things out. First of all, if you came with only 10 example images, then we don't even have a test set. So there'd be no way to even tell you, hey, this algorithm performs at a AP50 score of 90,
Mm-hmm.
because we have nothing to compare it with. So what we would do in that case is we would actually begin by probably simulating something that was less rare to see if we can get what the performances look like. So like if you say, hey, I'm trying to find ice cream trucks in Alaska, like, okay, we don't have very many pictures of ice cream trucks in Alaska, but maybe we have pictures of white cars in Alaska, mm-hmm. right? And so we'll use that as a stand-in and see how well we're able to do with that. Our experience is that synthetic data, when paired with real data for some of those, let's say, smaller objects on a geospatial scale, gives you sort of a 10 to 100x boost on any real data that you have. So the performance that you end up achieving would be, if you had 100 examples of your system, you'd get something like the equivalent of having 1,000 or 10,000 of them. Mm-hmm. And sometimes that's, that'll get you well into the 90s in terms of performance. Yeah. It depends on what you're trying to find. As the object scale grows, you're more likely to be able to do it with no real objects at all. So you're able to, in general, I'm speaking in broad generalities here, but computer vision algorithms do a better job of understanding structure as they have more pixels to work with. Mm-hmm. And so in those cases, we see a lot better results from pure zero shot. So you only need the synthetic data and you get to very, very high performance pretty quickly.
Right.
In practice, there are just a lot of ways in which people really do use synthetic data. So the other common scenario is, you've got 10 examples of something, okay? But you might be sitting on a data set that is massive because you've been collecting data for a while. It's just not annotated. So there could be more than 10 in there, but it'll cost you millions of dollars to have humans go hunt for the pixels to find them and build that training set. So in that case, what we've had some people do is build up even a low performing algorithm, say, an AP score of 50, but now they can run it on a million images. And they get to now a much larger number of real world imagery, and that allows them to bootstrap an algorithm, the whole performance. And they've taken a process that would have been millions of dollars and months of annotation and turned that into a few days, because now they can just, they're able to sift through and remove, 99.99% of what's in there. What's left, a human can go in and check.
Yeah, I think there was quite a good example recently tracking this balloon that was heading over North America. Somebody started with just a drawing and they used that to train a model that then I think found candidate examples and they trained a more accurate model and then tracked this thing. That's the kind of scenario you're talking about there.
That's exactly right. It's a great use case for synthetic data. Sort of the better the data that you have and the faster that you can put it into that type of application, the sooner you end up with larger data sets to train on.
Fantastic. Okay. That's been a really good introduction to the technologies. I definitely want to push in a bit more deeply onto the sort of boundaries of the usefulness of generative data. So there's been quite a few papers where people have used GANs to like augment data sets, and that presumably complements, the approach that you developed as well.
Yeah.
Maybe you can just sort of, compare and contrast those two approaches and maybe suggest when maybe a hybrid approach would make sense.
Yeah, the GAN-based approaches, or generative approaches broadly, or diffusion-based approaches are very, very powerful. But the drawback is that they don't do totally new things. They do variations. They can they can interpolate, but they can't really extrapolate very well. If that makes sense. So the ways in which we've found them to be useful in the types of real world business problems that people face, particularly in satellite imagery, is not in creating the whole image, but is in helping to create maybe more diversity in the scene. So if you say, hey, I have a car, maybe I have a 3D model of a car. Well, you may want to put all sorts of paint jobs on it, rust effects, snow effects, other things. Now, generative AI is a great way to do that. You can create those textures, you can apply them, you get something that looks pretty physically realistic, and you can apply that to that environment. And now you get 1,000 times more diversity. I mean, I'm just making up a number, but you get a huge multiple on the amount of diversity you can get from that object by using generative AI. But you're still going to turn around and simulate what that looks like under some physically realistic conditions. Does that make sense? So you still get that traceability and assurance of realism by using a physics-based model.
Yeah.
So that's just one small example of a place where generative AI sits inside of a workflow that includes some physics-based simulation, and then that allows you to get the physical accuracy, but also the traceability and history of what was actually produced.
Yeah, there's been a couple of papers about physics-constrained machine learning where somehow the outputs of models were input to another model, and then it was determined if it was a realistic output of a model, and then there was a sort of iterative process. I suppose something like that hypothetically might have a future in this domain.
Yeah, I think there's ways. There's certainly there's ways to assess whether or not a purely generative tool produced something that's physically realistic. I mean, but I think I almost feel like that's pointing out exactly the problem. Like, how much do you trust now that algorithm as to whether or not it's physically realistic? And so, that's the challenges are you're when you kind of interpolate between things that you've seen before, the points don't necessarily mean something that's physically grounded, and sometimes that's okay, but oftentimes it's not. Depends on what you're trying to do. In satellite imagery, because a lot of the problems that people really face are these rare object, rare scenario problems, or cold start problems where the sensor doesn't exist yet, so you don't have anything to feed the generative AI in the first place. Having a physics-based element is really crucial.
Fantastic. Well, thank you so much for this detailed insight into synthetic imagery. I actually wanted to end the conversation just with a slightly bigger picture question. Obviously, you work in multiple domains, not just remote sensing, but probably medical and others as well. I'm just curious where the remote sensing field sits compared to other domains in terms of their adoption of this kind of approach and overall kind of engagement with sort of AI and machine learning driven approaches.
Yeah, so the remote sensing industry broadly has been an early adopter of computer vision for years, right, for decades, really. And similarly, is an early adopter of synthetic data because they face these very large data problems. They face a constrained workforce really throughout, and they sort of intrinsically feel that need to generate insights as opposed to imagery. And so we started with remote sensing as our beachhead market. We found very receptive users within that market, have a lot of different clients that are doing all sorts of things there. And they're fun problems, right? They're also difficult and important to solve problems. So it's been a great place to be. I would say definitely leading the charge in many ways. Remote sensing and then autonomous vehicles are sort of like the other place where you see people really pushing the boundaries of what's possible with computer vision. And then I think what we're finding is the fast followers sit in security, like security imaging, cameras, airport scanning, things like that. Manufacturing is sort of up and coming quickly. Medical sees the need, but will take longer. It's just a highly regulated industry. And so that's one that we think has a lot of potential, but it'll take a little bit more time to get to.
Yeah. Well, that's a really fascinating insight. Thanks for sharing that. If people want to follow along with, I guess, your business and also your personal updates, where's the best platform for them to do that?
Sure. LinkedIn is where I think we're most active. So rendered.ai, you'll find us on LinkedIn. Of course, you're more than welcome to sign up for our newsletter as well from our website, www.rendered.ai. Really complicated stuff.
There you go. Awesome. Well, thanks again, and look forward to talking again soon.
Yeah. Thanks, Robin. Pleasure. Okay.